Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Our topic today will be triple integrals in cylindrical and spherical coordinates. All right, we talked about polar coordinates for double integrals in a previous section. These are two methods for triple integration that tend to make integrals easier in the case of certain surfaces and things like that. So let's see here. Cylindrical coordinates, we'll start there. The good news is there's not a whole lot new to this idea. In fact, it's merely a way to sort of extend polar coordinates into the third dimension. So this is really just polar coordinates in the xy plane with the z-axis attached. With the z-axis attached. So there's not a lot different going on here. You already know a lot about polar. In fact, even the integration is straightforward. So the picture, I'll put the analytics up here in a minute. There's z, there's x, there's y. Let's see here. So you are at a point x, y, z out here in space. And that means that directly, well, let me put that actually a little further in so I can make this look a little better. So there's your point, x, y, z in space. You can drop a perpendicular down. That's supposed to be a straight line, though it has some waviness to it. And then that should also be straight. It doesn't look like a very good right angle, does it? That's better. So there is perpendicular drop down to right angle, right? We know that every point in the xy plane can be defined r theta in polar coordinates. R is the distance out to the point. Theta is the angle it makes between 0 and 2 pi with the positive x-axis. So a point, x, y, z, becomes a point r theta z. Our usual polar relationships hold. X is r cosine theta, y is r sine theta, z is just z, right? And so this is the point r theta z there. And so, for example, we see that when I have r equals to c, this is a circular cylinder of radius c, right? So I'm asking about all points that have a given distance r from the origin. That is a circle in the xy plane. Extend that up into the z-axis, infinitely up and down. You do in fact get a circular cylinder, hence the name cylindrical coordinates. It's a circular cylinder, right? Okay, so how do we do integration on surfaces using this? We convert from rectangular to cylindrical using these formulas, just like we do from rectangular to polar, and then we just use an extra integrating factor. So your normal triple integral is something like triple integral over r f of x, y, z dv, right? And this is maybe dx, dy, dz, something like that. And this is in rectangular. And as we go, we convert, right? The region is now r. This is f of r cosine theta, r sine theta, z. And if you recall, in polar, we had to add in an extra factor of r. That exact same extra integrating factor shows up now for the exact same reason. This is r dz, dr, d theta. And remember this guy here, he's the extra integrating factor. Okay? So this is now in cylindrical. So there is your conversion, right? And this is the same thing. I mean, polar coordinates was useful for regions which had circular parts to them, circular circular pieces to them. They were circular in some sense. This is good for surfaces that have circular cross sections, something like that is especially useful there. Let's try one. That's cylindrical. Let's see here. An example. We could integrate over a cylinder that's been sort of indented in the bottom. So let's evaluate triple integral of r of the function x squared plus y squared to the 3/2 power. What do I want r to be? I want r to be the region bounded by the following surfaces. On the one hand, let's bound it by the cylinder x squared plus y squared equals 1. That's a circular cylinder parallel to the z-axis. Let's say, on the other hand, let's cap it off with the plane z equals 4. And let's put at the bottom of this cylinder, let's put a paraboloid. Z equals 1 minus x squared minus y squared. So somebody that has maximal point 0, 0, 1, then opens downward. So maybe we can draw this out. This is a beautiful drawing in the notes, maybe not so beautiful on the board. Let's see if I can recreate at least partially some of this thing. So maybe let's see here, you got something like this and then something cylindrical on the top, and it's coming down there. And let's see here, so it sort of extends like that. That's the front of it. This is already not looking nearly as beautiful as it should. I guess I really want this to be sort of over here, don't I? That looks better, and we can cap this off. Determined to make this look decent. And then internally this thing, there's this paraboloid. So this paraboloid is sort of sitting down in the bottom, right? And there is the other side of it, and sort of, let's see, let's see. And then the back of this guy sort of looks like this. So you have, there's the back of the cylinder. There's the paraboloid in the bottom there, right? So maybe this extends out like that. So that's the x-axis. That's the y-axis. Up here, out shoots the z-axis. Right, so this point here is 0, 0, 4. This point here is 1, 0, 0. And this cap here on this paraboloid is 0, 0, 1. Right, so basically this paraboloid is solid down here, it's capped, and so you imagine a cylinder that sort of has a capped bottom, like, what's like this? I don't know, nothing I can think of, but something that has a paraboloid at the bottom of it, something capped like that. Okay, so what we need here is and also this is sort of extending down. There, that looks not bad, not bad. So we need some limits here. We need the z, the r, and the theta limits. Right? Z is bounded between two surfaces. What is it bounded between? The top surface is the plane. The plane is the top cap. The bottom surface is the paraboloid. Right? So on the bottom, you're bounded between that and that, right? And in particular, we see that remember that x squared plus y squared is r squared, right? This is r equals c, the circular cylinder. So this is really 1 minus r squared is less than or equal to z is less than or equal to 4, right? That's the z limits. The r limits of integration, right? This thing is a circular cylinder of radius 1. So in the xy plane, the r limits are going to be from 0 to 1, right? It extends out from 0 and hits the wall of the cylinder, but goes no further than that. So this is the z limits. The r limits are going to be 0 to r to 1. And it's a full rotation around the cylinder, so your theta limits are going to be 0 to 2 pi. Right? And these bottom two guys are both in the xy plane. Right? Okay, so now let's set it up. Again, our function that we're integrating also is nice. It's got an r squared piece in it as well. So let me erase beautiful drawing, and we'll convert this guy. What we need to do. So this guy winds up being, we'll go dz, oopsies, or we'll go from outside to in, we'll go theta r z, 1 minus r squared to 4. This is r squared also, right? So this is also r squared. So r squared to the 3/2 power. Extra factor of r, don't forget about that. That's commonly made mistake. dz dr d theta. Again, I mean, switching r and theta doesn't matter. They're both constant limits. You can't put z past r, though. In other words, once you've dealt with r, if you still have z hanging around, you're going to end up with r's in your answer. That doesn't work. I mean, z has to be covered first. It involves the other variables. We always work and get rid of variable by variable as we do this process, right? So this is a 0 to 2 pi, 0 to 1, 1 minus r squared to 4. R squared to the 3/2 is r cubed, times r is r to the 4th. So this is a d, oopsies, not dr, dz dr d theta. Probably needs some more room here. All right, so we can now begin our integrating. Things look pretty easy to handle here. This is very easy to deal with, and everything else is straightforward here. This is just polynomials. So 0 to 2 pi, 0 to 1, right? This is r to the 4th z, evaluated from 1 minus r squared to 4, dr d theta. 0 to 2 pi, 0 to 1. Plug in, so I get 4r to the 4th minus r to the 4th plus r to the 6th. So 4r to the 4th minus r to the 4th is 3r to the 4th plus 4r to the 6th. 3r to the 4th plus 4r to the 6th. Did I get what I wanted to get there? Yes, I did. Wait, why did I have 4r to the 6th? No, I don't want 4r to the 6th. I want just r to the 6th. Yeah, I don't want 4r. Plus r to the 6th. That looks good, yeah. That is done dr d theta. Come over here. All right, so now 0 to 2 pi. Integrate. So what do we have here? 3/5 r to the 5th plus 1/7 r to the 7th, evaluated from 0 to 1, d theta. Right, so this winds up being 0 to 2 pi, 3/5 plus 1/7. What's the common factor? 35, so that's 21 35ths plus 5 35, 26 35ths. 26 35ths d theta. So 0, 2 pi, 26 35ths theta. Oopsies. Botched this up. 0 to 2 pi. And you wind up with what, 52 pi over 35? Is that what I have? Good, it is. All right, so there you go. So again, I mean, cylindrical coordinates are just a way for if you're in polar already and you are dealing with the triple integral, it may be that you want to use cylindrical. Again, we had a particularly nice pair of surfaces here. The plane is easy. This guy was a circular cylinder. That's great. The function we were integrating was also straightforward as far as a circular transformation. Had this been something weird, you might have had some difficulties there, but it turned out to be pretty good here. So, all right, so that was cylindrical coordinates. Let's talk about spherical coordinates now. And it should make sense that these are particularly useful when you're dealing with things that are spherical, right? So spherical coordinates is something that's a little bit new. It's more new than cylindrical was. Spherical uses 2 angles and 1 distance. Cylindrical used 2 distances and 1 angle. Right? So cylindrical used a distance for z, distance for r, and an angle theta. This uses 2 angles and 1 distance. So let me draw the picture here first, and maybe we can get some indication from that what's happening. So here is a point in space. This point x, y, z is going to become a point rho theta phi. Okay, rho is just a straight distance. So there is rho. So rho is just the distance from the point to the origin, i.e., that is to say, vector OP's length. If this is point P up here, this is P, x, y, z, right? Vector length from the origin. It's the length of that vector. And rho is a strictly non-negative quantity. Remember, r in polar coordinates could be negative. Sometimes you had a reason to define it that way. Didn't have to strictly be a distance. It could be the negative of 1 as well. Rho is strictly a distance. This phi is a little bit harder to get a handle on. Let me maybe switch to the red. So phi is the angle between the positive z-axis and this vector OP. So this is the angle vector OP makes with the positive z-axis. And in particular, phi is restricted between 0 and pi. How do I best explain this? So if you can imagine, so say the floor is the xy plane. I am standing parallel to the z-axis, right? As you point your arm out in some direction like that or like this or something like that, I make an angle with my torso, right? In other words, if it's like this, I'm parallel to the floor. This is pi over 2. Like this, maybe it's pi over 4. Maybe now it's pi over 6. Pi over 3 is a little bit lower than that, something like that, right? So I have an angle, right? So if the vector OP lies in the xy plane, the angle is pi over 2, the same way that my angle straight out is pi over 2, like this, right? And if I point straight up, my angle is 0. If I point straight down, my angle is pi. Right now, my arm is parallel and pointing in the direction of the positive z-axis, parallel pointing in the direction of the negative z-axis, right? So as I rotate this thing around, it doesn't matter which side you're on. That's what doesn't matter here, whether you're over here. This is quad 1, quad 2, quad 3, and quad 4 back here, right? Doesn't matter which side of the z-axis you're on. So let's see, how flexible am I? Not very, but if I had my arm out like this, right? Now I'm parallel behind me. This is still a pi over 2 angle with the floor, right? It doesn't matter what side of me the arm is on. It's inconsequential. If this is on the positive z-axis and pointing that direction, or on the positive z-axis, this is going to be 0. If it's on the negative z-axis, it's pi. If it's on the xy plane, it's pi over 2. If it's between, it's something between those guys. That's how phi works. And theta is just good old theta from polar and cylindrical. So this is the angle from cylindrical coordinates. This is the angle from cylindrical coordinates. And of course, that can range between 0 and 2 pi. And let's see here. What do I want to say about this Nothing right now. Okay, let me draw some typical surfaces in these. I didn't draw theta on here, did I? I didn't finish my picture. So the picture keeps going like this. You have somebody, and then you have a perpendicular up here, and so this guy is like that, and there, and then that angle there. That guy's theta, right? So that is from x, y, z to p theta phi, like that. Right. Okay. All right. Let's see here. Some typical surfaces in spherical coordinates. If rho is a constant, this is a hollow sphere, right? So I mean, if rho is a constant, you want all points that are distance constant from the origin. That is a hollow sphere. So there maybe is your point, and something like that, maybe, I don't know. So then this thing is looking spherical, right? So something like that. So there's a lousy sphere, but it's a hollow sphere with center of the origin and radius equal to c. What if phi is equal to c? So this is hollow sphere. Hollow sphere. Then this is actually a hollow half cone. Right? In the sense that, I'll draw a picture first. So the z-axis comes up like that. You're down there. All these angles, right, have angle between them equal to c. Or all these points, sorry, all these points have angle between them and the positive z-axis equal to c. So think about it here. As I have a fixed angle, right? In other words, if my arm is like this, right? If I were to extend my arm out, right, you would have points that would go up and up and up on one side of the z-axis. And on the other side, you could also, imagine sort of turning yourself, and now you're facing like this, and now your arm goes up like this, right? Now you're going out the other direction. So you have two line segments, and all the points on those line segments are going to be the same angle with the positive z-axis. And again, it doesn't matter what way I orient myself. So whether I'm facing this way, and I could put my arm out, and let's see if I can not knock the board over. But if I turn myself, right, I move in a circular motion, I'm rotating the axis, right? You see that all these points are sweeping out a circular arc around me, right? So my arm is a fixed angle, and I sweep out a circular arc as I rotate around the z-axis. That's why this is a hollow half cone. And this top guy here is when phi is between 0 and pi over 2, because you're above the xy plane, and if you're below, then you look something like this. So there's your hollow half cone, and this is atrocious drawing, but yeah. So your cone sits there, and so you extend down, and now your angle goes like that, right? So now I'm below 90 degrees. I'm down here. I'm rotating around, sweeping out a circular arc with my arm in a fixed position. Okay. So this is pi over 2 less than phi less than pi. Okay. That's phi equals c. And if theta is equal to c, it's all the points that have angle theta in the xy plane. Well, that produces a vertical half plane, right? In other words, this entire plane extends up forever and ever and ever. So you have something that looks maybe, so there's x and y. Maybe here's a point, right? Maybe that's angle c, and then this thing goes up forever and ever. Right, so there's a vertical half plane that equals c, vertical half plane. All right, so there's that. So again, I mean, simplest surface is going to be something like a hollow sphere, hence the name spherical coordinates. All right, the relationship between rectangular and spherical. It's not entirely obvious. A little trig brings it out rather quickly, though. We're going to probably need to use, what do I have all these things drawn over the place for? So we'll need to use some different colors here, maybe. So let's see here. So I want, let's see. There's rho. Let me draw, here we'll draw that, because it's going to extend up nicely, yeah. So there, that's a right angle, right? Let me draw phi and theta on here in red. So there's phi, there's theta. Right? We see right away that, and then this is r down here, isn't it? Yeah, that's r from polar coordinates, same polar coordinates are, right? We see right away that I can sort of make a sketch here. Running out of room there, but we can kind of complete that parallelogram, and that's a right angle there. We see that for this triangle here, that's rho is the hypotenuse, so that cosine phi, right? So let me put the z down here so you don't get confused between what I'm talking about. So this is my distance z, all right? So my z position here, right? This is x, y, z. My z position is a rho cosine phi, right? Because cosine phi is rho, or is z over rho, right? So you get that relationship. And r down here, what else do I want to add to this picture? Let's see here. This over here is also phi, isn't it? Yeah. This angle here is also phi, yes. That angle there is also phi. And so as a consequence, now here's rho sitting up there. Now r is sine, or is a rho sine phi. Right, so r is rho sine phi. Right, r is rho sine phi. And since we already know from polar, x is our cosine, y is our sine. What we get out of this all together, so you put all these guys together, you get x is rho sine phi cosine theta, right? That comes from plugging this in for r. You get y equals rho sine phi sine theta, right? And then z is just what it is. It's just rho cosine theta. Oopsies. Rho cosine phi, I'm sorry, not cosine theta. Rho cosine phi. And we notice that if we take x squared plus y squared plus z squared, right? Polar x squared plus y squared is r squared, x squared plus y squared plus z squared here. Take a look. We have a rho squared, sine squared phi, cosine squared theta. Rho squared, sine squared phi, sine squared theta. And a rho squared, cosine squared phi, right? So we have the sine squared, well, I better maybe do this. Rho sine squared phi cos squared theta. Rho squared sine squared phi sine squared theta. Rho squared cos squared phi, right? And let's see here, out of the first two guys, You can factor a rho squared sine squared phi, right? And you're left with cosine squared theta plus sine squared theta, and then plus, and here we go, rho squared cosine squared phi. This will cancel to 1, right? Now you got rho squared sine squared phi plus rho squared cosine squared phi. That is rho squared. So in fact, x squared plus y squared plus z squared is rho squared. Right? That is the equation of a sphere. Okay. So what about doing integrals with this? Let's talk about the integrating factors. The derivation is probably in most books. It's not, I'm not going to do it here just to save ourselves a little bit of time, but it is worth looking at maybe once. All right, so you're in rectangular here. How do you convert? Right? Remember, x is rho sine phi cos theta. Y is rho sine phi sine theta. Z is rho cos phi. And then the extra integrating factors end up being this factor of rho squared sine phi. So again, we're not going to derive this, but certainly any book worth its salt will have a discussion of this. And it's because of just the same general reason why the extra r is there in polar, because you have not in this case polar rectangles, but somewhat spherical rectangles, right, guys, that sort of look more and more spherical the smaller and smaller they get, and they have this extra amount of volume change they're adding in, so this extra factor. And this will all actually become fairly clear in the next section. We talk about substitution. And getting these results is actually pretty easy to do with one blanket idea of the Jacobian, but make sure you note those additional factors. So that's kind of a long thing, but I mean, you know, just plug in and use extra factors and you're in good shape. Okay, let's do an example. Let's find a volume of a solid inside the cone z equals square root x squared plus y squared, and below the sphere x squared plus y squared plus z minus 1/2 squared equals 1/4. Okay. I don't want to draw the picture yet, do I? No. Right. Okay. So this sphere, right? The sphere has center 0, 0, 1/2, and it has radius 1/2. And let's see here, what can we do? We can expand this out slightly, I guess, make that interior term. So if I do that, I get x squared plus y squared plus z squared minus z plus 1/4 equals 1/4. And let's see here, that boils down to just x squared plus y squared plus z squared equals z. Right? That's the sphere, right? I just expanded this out, FOILed it out, and I got this, right? And it turns out this may be actually more useful to have because we have an expression for z, but it's sort of less, and we don't have to worry about doing things like squaring it out when we have nasty things like sines and cosines, and then we don't want to deal with that. Okay, so if we convert to spherical, what do we get? X squared plus y squared plus z squared is rho squared. We saw that last time. Z is rho cosine phi, right? Z squared. Well, z is rho cosine phi, right? On this sphere, the point 0, 0 is on there because your center is at 0, 0, 1/2. But as long as you don't have that point in question, you can say this is just rho equals cosine phi. So there is your sphere in spherical coordinates. This is rho not equal to 0. Rho not equal to 0, because you can't divide by 0. How about the cone? So that's the sphere. So the sphere is done. The cone, let me erase this and leave the top part. So the cone is a rho cosine phi, that's z, and square root of x squared plus y squared. So let's hash that out. In fact, what's even better, maybe, what's probably even better actually is just recognizing that's r squared. Yeah, so I did it probably too slowly here. We can recognize it's r squared, right? And we know what r is. What do we have r as? Rho sine phi. So this is rho squared sine squared phi, like that, right? And this cone is going to be being rho sine phi. We know rho squared is okay. Sine squared phi, sine phi between 0 and pi is positive, so you're okay with that, right? Since phi is between 0 and pi, so there's no question about this being plus or minus there. We're in good shape with that, right? So what we have here is rho cosine phi equals rho sine phi, right? We can cancel out the rho's, right? Again, the point 0, 0 is the one guy on this cone that is slightly, that causes it to be hard to cancel out those rho's, but we get cosine phi equals sine phi for every other point, right? The cosine of phi equals the sine of phi exactly at which angle in here? Pi over 4, right? So this implies pi over 4 is the value of phi. And that should make sense. Remember that phi equals the constant was a hollow half cone. So we have a cone here. All right, so this is the cone in spherical coordinates. This is the cone in spherical coordinates. In fact, in both cases, even the cancellation of rho wasn't a big deal because this does include the point 0, 0, and in the previous case with the sphere, let's see, the sphere was what? Rho equals cosine phi, and it was it included the point 0, 0, so at the angle 0, then your rho would in fact be 0. So it's okay, it includes them both. Yeah, so that point's not missed either. It's not a concern here. So this was the sphere, this was the cone. Okay, and the picture looks sort of like this. Let's see here. So here's go to the bottom, and this is truly the ice cream cone function. So there's the walls of the cone. They're extending like that, right? And the sphere is, I'll put it in red here. So the sphere well, it sort of missed the cone a little bit, didn't it? But we can fix that. There. So the sphere looks something like that. There. Oh, well. Close, but good enough. Yeah, so there's a sphere, right? And what I care about is inside the cone and below the sphere. So this stuff out here is outside the cone. once the cone gets past the sphere, don't care about that either, right? What I really care about is the interior of, so this is below the sphere, right, and inside the cone, right? So in other words, this truly is an ice cream cone styled surface, in that what you have here is things that are capped off up here, and they're also inside. So this entire area inside the cone is considered, and also the area that is above, that bubbles out over top of this sphere as well, because it is inside the cone's range. So imagine an ice cream cone with, you know, ice cream atop it. That's what you have here. You have that kind of a surface, right? Okay. Let's see here, and these are circular cross sections down here inside the cone. How about some limits? Rho, well, rho ranges from 0, and so there's rho equals 0 down at the point of the cone, right? And then the top of the sphere is as far as this goes, right? In other words, the distance from these points can extend all the way out to the top of this sphere, and the sphere is not just a constant, right? I mean, if it was centered at 0, 0, it would be a constant, centered at 0, 0, 0, but it's not. It's variable, right? So it ranges from 0 at the origin to the top of the sphere. In other words, the top of the sphere is variable. It's cosine phi, right? Because where's the sphere? Rho is cosine phi, right? So the rho values are changing depending on the position of phi there. It depends on phi, right? So rho is a function, or its distance, its limits are a function of the variable phi. How about phi? Well, phi ranges from 0. Again, there's that point on the z-axis, and you extend your arms out either direction. How far do you go out? You go out pi over 4, right? So phi goes to the edge of the cone, which is pi over 4, right? So your phi range is from 0 to edge of the cone at pi over 4, right? And your theta range is 0 to 2 pi, because those guys are circular cross sections. Everybody's hit in here in a circle. This doesn't look very circular, but it should. And theta is from 0 to 2 pi. Right? So this guy has a circular cross sections. Circular cross sections. And so there's your limits. So your limits are 0 to cosine phi, 0 to pi over 4, 0 to 2 pi. So you have some flexibility here in whether you want to do phi or theta last, as long as rho goes before phi. Right? In other words, as long as you've dealt with rho before you hit phi, you're in good shape. What am I doing here? Yeah. So the volume, all right. Integral, 0 to 2 pi, 0 to pi over 4, 0 to cosine phi, right? We're integrating the function 1, but there's always the extra integrating factors inherent here. Rho squared sine phi d rho d phi d theta, like that. Okay. What do we have here? 0 to 2 pi, 0 to pi over 4. Integrating this guy with respect to rho is a 1/3 sine phi rho cubed from 0 to cosine phi d theta, right? So you integrated rho first. All right, plugging in, what in the world do I get? So I get 1/3 sine phi cosine cubed phi d theta. Again, this cries out for substitution. U is cosine phi, du is minus sine phi d phi. All right, so you crank that thing out. I have my 1/3 in it, don't I? Yeah. Everything looks all right there. This ends up being what? Minus a third integral from 0 to 2 pi. We get 1/4 cosine to the 4th phi from 0 to pi over 4, right? Because we're integrating u cubed, right? We're integrating u cubed and tacking on a minus out front because this had a minus up here, right? Remember substitution. And what happens now? Minus a third, 0 to 2 pi integral. Slap in pi over 4. The cosine of pi over 4 is root 2 over 2. If you hit that, that gives you 4 over 16, which is 1/4. So that should be 1/16, and then minus a 4th. Right, which is, let me think here. Wait a minute. Hold on a minute. So cosine pi over 4, right, do I have everything what I want here? Right, so cosine pi over 4 is root 2 over 2. If you take that to the 4th, you do get 4 over 16, which is 1/4, right? So you get 1, and then multiply that by 1, so you end up with 1/16, and should end up with minus a 4th. Right, okay. So that's yeah, okay, so it is right. Yeah, okay, negative 3/16. I have what I wanted. Good, negative 3/16. This is also d theta. D theta, and this is, what on earth is it? It's 1/16 times theta, 2 pi to 0. So that is, what is it, pi over 8? Yeah, pi over 8. So there you go. Okay, that's it.